Hello students, welcome back to the lectures on principles and chemical applications of thermodynamics. And today we are going to talk about the second law of thermodynamics and introduce you to the concept of entropy. But before we pass on to the second law, I must point out that the first law of thermodynamics indeed gave us a very fundamental advantage in the sense that it introduced us to the concept of internal energy and enthalpy. And it also told us that we can think of our universe as follows. It was assumed that the universe is comprised of the system and the surrounding as shown in this figure. So here I have system which is a part of the universe that we are interested in, and the rest of the universe which has been colored by blue in this picture, this is the surrounding. And together this whatever is there colored in blue and the green ball, that is the system and the surrounding, constitute the universe. Of course, we do not have complete knowledge about the universe. Therefore, to start with, we have to make some assumption, and it was assumed that the universe is isolated. If that is so, then what is the immediate consequence? If this system is undergoing any change in state that results into its having a change in internal energy, then I must be able to write the following equation. So du system is the change in internal energy of the system, and the corresponding change in internal energy of the surrounding is du surrounding. Now, if I add the two quantities up, that must be giving me du universe. And since universe is isolated, therefore, it is expected that du universe must be equal to 0 during any change in the state of the system, which might involve exchange of internal energy between the system and the surrounding. However, irrespective of how much energy has been exchanged between the system and the surrounding, the total energy of the system remains constant, and therefore du universe is equal to 0. And we also understand this then formally. A system needs to undergo a change in state in order to transfer energy between the system and the surrounding. But under such condition, the total energy of the universe will remain constant. Now, although the first law of thermodynamics gave us a lot of fundamental concepts, but there are certain limitations of the first law that I would like to focus upon in this slide. First of all, if I ask the question, yes, I do understand that a system can undergo a change in state, but will this change in state take place at all when I am making an observation on the system? If yes, if this change in state happens indeed, then what would be the spontaneous direction of change? And then if the system starts changing its state from one in equilibrium state, what would be the new state where it attains equilibrium again? So when the equilibrium is attained under the new conditions, obviously the system properties will become independent of time once more. So I can say the change that was taking place has now stopped. So under what condition will this change in state stop? Let me take an example and explain this to you. Let us say that I take a specific example of the passage of a system from an initial equilibrium state to the final equilibrium state. So this is my system in its initial equilibrium state, where I have a fully insulated rigid box where this gray wall is impermeable to the gas which is confined within. The internal volume of this box has been divided into two parts by using a separator as shown here. On the left hand side of the separator, I have an ideal gas, and on the right hand side of the separator, I have a vacuum. So if this is the initial equilibrium state, then by construction or by the design of the experiment, the ideal gas cannot exchange energy, volume or particles with its surroundings outside this entire box. It also, if I make this separator adiabatic, rigid and impermeable, it cannot exchange energy, volume or particles with that side of the compartment that is evacuated. Now I am going to induce a change in state of this particular system. The way to do it is, now I am holding the gas confined to this red region of the box. I am going to withdraw the separator adiabatically from between the red part and the evacuated part. What will happen now? First law will tell you that yes, the gas will no longer be at equilibrium, but it will undergo a change in state. Of course, if I perform this experiment, the gas will indeed undergo a change in state. Then my question is, what can this gas do under the given condition? Actually, there are many things that the gas could have done. It could have compressed and went and occupied a smaller volume like this, or it might have decided to curl up in a ball in a compressed state and occupy a small volume in this box. Or maybe the system would have decided to undergo expansion, but after it starts expansion and it occupies about 60 to 70% of the volume of the box, it stops. It doesn't want to go anymore. Or maybe it has expanded, it has occupied about 80 to 85% of the available volume and then decided, no, I don't want to go anymore. Or will the gas expand and go all the way and fill up the entire available volume that is provided to it by this insulated box? So this is a typical experiment, and a typical experiment where a thermodynamic change in state is affected. You have prepared an initial equilibrium state with a constraint such as the adiabatic wall that I have drawn here. Then you withdraw this internal constraint and allow the system to undergo a change in state. Now, first law of thermodynamics does not tell you whether the gas is going to compress or expand. But if you carry out an experiment, actual experiment, what will you see? You will see that none of the lower pictures are possible. The gas will expand, and therefore expansion is the spontaneous direction for the change in state. And it also tells us the final equilibrium state is reached when the gas has occupied the entire volume of the box. The first law doesn't tell you why compression will not occur or why any of these scenarios are not observed in the experiment. So this is where the second law of thermodynamics was required. The second law of thermodynamics told us that a spontaneous process occurs naturally and needs no external source of work. A non-spontaneous process, although allowed by the first law, requires an external source of work to drive it. which means in the previous example, if I wanted to compress the gas, I will have to do some work on the gas to compress it. It will not undergo a spontaneous compression under the given experimental condition. And therefore, I would say that the second law of thermodynamics tells us the direction of a spontaneous change in state and the new equilibrium state that will be achieved at the end of the change. Now, all these did not come naturally when people were doing experiments on the macroscopic systems that they were interested in. They were actually interested in converting heat into work. So if you think of the application of first law to this problem, you understand that if I can carry out a cyclic process on a system, and in this process I supply some amount of heat Q and require it to perform some work W, then since it is a cyclic process, delta U will be equal to 0. And then the first law tells you that Q would be equal to minus W. And therefore, the conclusion from first law is that heat supplied to a system can be completely converted to work. From the very beginning, I have been mentioning again and again that I would like to harness the energy of a given system. I feed it a little and make it do some useful work for me. So if it so happens that whatever I give as input is converted to useful work as output, that should be the ideal condition. And therefore, one was interested in testing such possibility by the construction of heat engines. So what are heat engines? Heat engines are the instrument or the machine that we build for outsourcing the work that we need to be done without doing it ourselves. And of course, for the perfect heat engine, I must be having 100% efficiency. So what is eta? Eta is the efficiency, where this is equal to modulus of work done divided by the input of energy that you have given to run the engine. Therefore, first law, as shown here, predicts that construction of such an engine is possible. So let me look a little more into how a heat engine converts heat into work. So by definition, an engine is a device or system that converts energy to work. A heat engine draws heat from a hot reservoir, converts some heat to work in the surrounding, and releases some heat to a cold reservoir. The engine itself is a system that undergoes a cyclic process. Now, what is a reservoir here? A reservoir is a large body whose temperature does not change when it absorbs or gives up heat. Now, this is a picture showing schematically a heat engine. So, this heat engine works in a cycle whereby in one step it absorbs this amount of heat QH from a high temperature reservoir. It performs some work W on the surrounding, and then it rejects some heat to a low temperature reservoir or a cold reservoir. So for this heat engine, what is its efficiency? As I have said, efficiency is the ratio of output divided by the input. So here output is the amount of work done, which for the sake of clarity we are writing as the magnitude of W. And what is the amount of energy that this system has taken? That is QH, that is the amount of energy that it has absorbed from the hot reservoir or the high temperature reservoir. So of course, this is what I want. I want a perfect heat engine. That is simply because, as the famous cartoon character Calvin says, happiness isn't good enough for me. It's not enough that I have a heat engine converting heat into work, but I demand euphoria. I demand the perfect heat engine. And unfortunately, life is not fair. So even if little Calvin, a very naughty 6-year-old boy in the cartoon created by Bill Watterson, here comes the Kelvin's statement of the second law of thermodynamics. It says it is impossible for any system to operate in a cycle that takes heat from a hot reservoir and converts it to work in the surroundings without at the same time transferring some heat to a colder reservoir. Of course, now we understand where the problem is. Yes, I would like to have my system operate in a cycle. Why is that so? If you are driving a car, for every time you press the accelerator, you don't want to run to a nearby garage and get the engine replaced. So your engine has to be able to work again and again, which means the engine has to work in a cycle. Now, when it is working in a cycle, it is taking some input energy in the form of heat from a hot reservoir. And it will also convert it to work in the surrounding. So if you are driving a car, it will be moving the wheels so that you move forward or backward, whatever way you are driving it. But at the same time, it has to go back to its initial state of the cycle. And there we find that it has to transfer some of the absorbed heat to the colder reservoir, and you cannot do without this. But why does it lead to eta less than 1? So let us have a look at why I'm saying that in a cyclic process like this, a heat engine will operate with less than 100% efficiency. So for a cyclic process, delta U equal to 0. That is because U is a state function. So from first law of thermodynamics, we understand that W would be equal to minus of Q. And what is Q? Q here is the total amount of heat exchanged during the cycle. So if you think about this cycle, there are two instances of exchange of heat. One is QH, another is QC. This is the amount of heat exchange between the system, that is my engine, and the high temperature reservoir. And this is the amount of heat exchanged between the engine and the cold reservoir. Therefore, I will replace Q with QH plus QC. Now, if I write down what eta for this engine is, what I find is this now can be written as QH plus QC divided by QH. And I do a simplification and I come to this expression that eta is equal to 1 plus QC by QH. Now think about the sign convention that we adopted when we were discussing the first law of thermodynamics. If the heat exchanged goes to increase the internal energy of the system, it is positive. So when the system absorbs heat, Q is positive. Now in this cycle, where did the system absorb heat? It absorbed heat from the high temperature reservoir, and therefore by my sign convention, QH is greater than 0. When the system gives out heat or releases heat into a low temperature reservoir, that is where QC must be less than 0. And the consequence is then that the ratio QC by QH is negative. And therefore, I would say that eta is always going to be less than 1 as QC is less than 0. Of course, initially this might sound a bit confusing, but as you will see, as we probe deeper into the second law of thermodynamics, we would understand the fact that why we cannot construct any engine where I just get rid of this step. The Kelvin's statement of the second law of thermodynamics says that you cannot construct an engine that will do without this step. Or in other words, QC is always not equal to 0 and QC is a negative quantity. And this will always ensure that your engine that operates in a cycle will operate with less than 100% efficiency. Now, so basically the idea was we have to look for a new system property that will decide the direction and the end point of a spontaneous process, and that should also tell us why I am unable to have heat engines with 100% efficiency. For this purpose, let us have a closer look at the heat engines again. Now, this is the reversible engine which was designed by the French engineer Sadi Carnot long back, and this is known as the Carnot engine. So, a Carnot engine operates in a reversible cycle and uses an ideal gas as the working substance. So let us have a look at what happens to this engine at different stages of its work. So when we start this operating this engine, we start from this point A, and then we make the gas undergo an isothermal expansion at a temperature T, H. It is kept in contact with a high temperature reservoir whereby it takes QH amount of heat and it expands isothermally from the state A to the state B. Okay, so this is the step where the system, when kept in thermal equilibrium with a high temperature reservoir, is absorbing QH amount of heat. Then we take this cylinder of gas and put it in isolation by covering it up with insulated material. Now what will happen to the system? The system will then undergo an expansion, but according to the given condition, it will be an reversible adiabatic expansion. Since it is adiabatic, no heat will be absorbed during this change in state, although there will be a change in volume from this value to this value. Now, once I have reached the volume corresponding to the point C, then I will take this system, take away all the insulation around it and put it in thermal equilibrium with the low temperature reservoir or the cold reservoir. When the system is in equilibrium with the cold reservoir, what will happen? It will undergo an isothermal compression so that it goes from this high value of volume to this low value of volume characteristic of the point D. And in this process, it is going to give out QC amount of heat to the cold reservoir, which is at a lower temperature compared to the high temperature reservoir. And now you will have to bring the system back to A from D, and this is done by carrying out an adiabatic compression whereby the volume of the gas goes from that characteristic of the point D goes to the point A. So the engine is back to where it started from. Now, if I look back and try and find out what the different quantities involved in such cycles are, I understand that when I have a step A to B, it is an isothermal expansion from a volume VA to VB. So this must be the amount of work done in this isothermal expansion process at a temperature TH. I can also find out the amount of heat absorbed by the system during this process. Since I'm using an ideal gas and it is an isothermal process, I must be having delta U equal to 0. Similarly, I also can find out these quantities for the steps 2, 3 and 4 and evaluate what is going to be the total variation of these quantities. So if I ask what is the total amount of work done as the engine starts from A, goes through B, C and D and then comes back to A. So there are 4 types of work done here, and so the total amount of work done would be a summation of these two. And as you see here that the work done in step 2 is exactly equal and opposite to the work done in step 4. And therefore, the total amount of work done in this cycle turns out to be the summation of the work done during the isothermal expansion of step AB and isothermal compression of the step CD. Similarly, you can find out this is the total amount of heat absorbed, and since U is a state function, as expected, if you add up all these 4 changes, you end up with delta U cycle equal to 0. Interestingly, if I calculate Q reversible by T for each of these steps, in the first step when the system goes from A to B, all I'll have to do is, this is Q reversible, I divide it by the temperature at which the exchange of heat Q reversible took place. So I'll have to divide this quantity by TH, the temperature of the high temperature reservoir, and the result is nRln Vb by Va. Now, in the stages 2 and 4, Q reversible is equal to 0. 2 and 4, the Q reversible is equal to 0 because these 2 stages are adiabatic changes. So, by definition, Q reversible are going to be equal to 0. So, the value of this quantity Q reversible by T are going to be 0 in these 2 steps. But if I look into the third step, which is once again an isothermal compression involving the exchange of heat QC, you understand that if I take this Q value divided by the temperature Tc at which this exchange of heat has taken place, I am left with this quantity. So what is the total value of Q reversible by T in this cycle? When I add them up, and note that because these are the 2 adiabats connecting the states AD and BC, I must be having ln Vd by Vc equal to ln Vb by Va, and therefore a summation of these 2 terms will turn out to be 0. Now, I would like you to compare these 2 entries in this table and derive a conclusion. The conclusion is, over a cycle, it is only a state function that gives you 0 change. Here, in addition to U, I have found out another quantity which is Q reversible by T. Therefore, this must be equal to some delta S, where S is a system property. S was given this name entropy which was not known in the first law of thermodynamics, and that introduced to us the concept of a new state function, entropy, about which we are going to learn a little more in the next lecture. Thank you.